Hi everybody, how are you doing? Welcome back to my SP2 channel. So you probably remember in our previous lecture, we talked about the Electron configurations and I promised you to go over a bunch of practice with you. So this video is all about the practice on Electron configurations. We're going to have two sets. There are going to be a bunch of examples on the regular Electron configurations, the normal ones, and then we also have a couple of anomalous Electron configurations, okay? Okay, so we're going to be using our periodic table, right, for all of these practice. Remember, your reference is going to be the table. There's no need to memorize any of these values or any of these orbitals, right? We always need to go back to the table, right? That's something that we always have access to that to be able to express the electron configuration, okay? Okay, so here's the first one. Write down the electron configuration for lithium atom. So we're going to find lithium first. And as you can see, you've got it over here. Hello, lithium. We have 3 electrons. And I can start by writing my full configuration for you. And then we can take a look at the condensed one as well. Okay, so starting from the very first orbital, which is going to be our S, and I have it on 1s, right? So it should be 1s2. And then we're done with the first row. You're looking at the second row. We have 2s, and there's only 1 electron here, right? So 2s1, and we're done. Now, I can also write it down with the help of the previous noble gas configuration, right? So the noble gas to the previous row is going to be helium. That means you can write square bracket helium, right? And then I have 2s1, okay? So the first one is going to be the complete electron configuration, and the second one is like condensed form, okay? Okay, so looking at the second one, write the electron configuration for phosphorus. We're going to find phosphorus first. Hello, you are here. We have 15 electrons for you. And I'm going to start by writing the full configuration. And that will be 1s2. Looking at the second row, we have 2s2 and then 2p6, right? We're done with the second row. Looking at the third one, we have 3s2, and then I'm looking at the p section. There are only 3 electrons here, so that should be 3p3, okay? Now, if you look at the previous row, the row above that, then we're going to get neon as our noble gas. So that would take care of all of these core electrons, right? And then I can continue writing my valence electrons, which is going to be 3s2 and then 3p3. Okay, cool, cool. The next example is for vanadium, which is one of our transition metals, and we have 23 electrons here. Okay, so if that's okay, we're going to stick with the condensed form just because we have so many electrons, right? So it's going to be vanadium. And then I have the previous noble gas, which is the noble gas in the previous row, and that is argon. Okay, and then you are on the 4th row, so 4s2, and now slow down. Okay, so if you remember, after we're done with the 4s, we have to go 1 row down for the d orbitals, and that should be 3d, and then I have 3 electrons, right, for my vanadium in the d orbital, so that should be 3d, 3. Okay, excellent. The next one is going to be for uranium, which is one of our F block elements. So it's a little bit harder. You've got 92 electrons here, right? Okay, so the previous noble gas for uranium and all of the elements on this row where they belong to n equals 7 is going to be radon, right? So because radon is the noble gas in the previous row. So I'm going to go by uranium, and then I have the square bracket radon. So that means we're done with all of our core electrons, okay? And then we're going to continue on 7s2, right? And now I need to go 2 rows down for the F, right? And 1 row down for my D. So there is a D for sure, which is going to be 6D1. And then I have 7 minus 2, which is 5F. And you count your F, which is going to be 1, 2, 3. So that would be F3, right? So this would be the electron configuration for uranium. Okay, I hope that makes sense. Looking at the next page. Okay, so now we're going to be looking at some of the cases that are unusual. So anomalous electron configurations means that they're not following the rule, okay? They are having a slightly different, distribution for the electrons. And the first one, the first exceptional case for us is chromium. So take a look at chromium. If it was usual, okay, if it was usual, then it would be chromium. The previous noble gas is argon. And then I have 4s2, right? And then I have 3d4. So if it was usual, then I would be something like this. Now that I know my chromium is one of the exception, I'm going to explain for you what exactly happening here. So think about your 4s and your 3d energy levels. So we know that the 4s energy is less than the 3d. But you can imagine that they are close enough to each other so that one electron can jump from the 4s to the 3d to make it d5. So what we're going to have here is we're going to have chromium as argon, and then 4s1, 3d5. Okay, so what's the reason for that? If I have 3d5, that means every single d orbital has only one electron. I don't have the two of them within one orbital. That means you can minimize the repulsion between the electrons, right? And that is a great idea because you can stabilize your configuration. So the only reason that 4s1 3d5 is more stable than 4s2 3d4 is because of not having any two electrons within one orbital of the d sections. Okay, so we call that half filled subshell, which is a lot more, stable, and naturally you're going to see chromium in this form. So the final answer for chromium would be this configuration here, right? This is not existing. We're not going to have 4s2 3d4. Okay. Okay, so kind of similar situation is what we have for copper. So let's take a look at copper here, which is 29 electrons for that. And as you can see, there's only one element after copper to finish your D section. Okay, so if copper was normal, right, then you would go by copper, and then I have argon, 4s2, 3d9, right? Now, what happened here is, for the same reasoning as we have these two 4s and 3d energy levels that are close enough, one electron can jump from the s to the d orbitals in order to complete your d section, right? So we're going to have argon, and then 4s1, right? And then I have 3d10. So this would be the configuration that we expect to see for copper, and the 4s2 3d9 does not exist. Okay, I hope that makes sense. Okay, thank you very much for watching this video. If you like it, give it a thumbs up. There's going to be more practice for you for sure coming up. There are going to be more lectures, and I'm really happy that you guys are supporting me. Excellent. Take care of yourself and see you soon on the next video.